Easter Island or Rapa Nui lies as an isolated speck in the vast expanse of the South Pacific, more than 3,500 kilometers from the nearest continental shore. Its remote location has long fueled fascination and speculation among historians, archaeologists, and travelers alike. Despite its small size, just under 165 square kilometers, the island houses one of the most mysterious achievements of ancient human civilization, the colossal Moai statues. These monumental figures carved from volcanic rock stand as silent sentinels across the landscape, their towering forms capturing both the imagination and the scrutiny of modern researchers. The Moai vary considerably in size, with most ranging between 4 and 10 meters in height, while some of the largest reach up to 22 meters when including their platforms or ahu. Their weights span from 10 to over 80 tons, presenting an extraordinary engineering challenge for a society without wheels, draft animals, or iron tools. Each statue was painstakingly carved from volcanic tuff at quarries such as Rano Raraku, where the soft yet resilient stone allowed skilled artisans to shape intricate features with remarkable precision. Facial expressions, elongated torsos, and finely detailed hands and ears all testify to a sophisticated understanding of both aesthetics and stonework, reflecting a culture that valued craftsmanship, social symbolism, and spiritual significance. The Rapa Nui people, the indigenous inhabitants of the island, developed a highly organized society with complex social structures and elaborate ceremonial practices. Oral traditions, mythologies, and ritual observances were intertwined with daily life, providing guidance for agricultural practices, navigation, and communal construction projects. The Moai themselves were more than artistic expressions. They embodied ancestral power, providing spiritual oversight for villages and reinforcing clan hierarchies. Their positioning, typically facing inland, suggests a deliberate strategy to watch over and protect the settlements, linking each statue not only to its physical location, but to the social and religious fabric of the community. As one surveys the island, the distribution of Moai along coastlines, plains, and hilltops evokes a carefully orchestrated plan. Quarries, transport routes, and ceremonial platforms appear interconnected, hinting at an advanced logistical system. The fact that some statues were transported several kilometers across rugged terrain, including hills and valleys, emphasizes that the Rapa Nui possessed not only physical endurance, but also exceptional problem-solving skills. Every Moai represents an achievement in both engineering and social coordination, a silent testament to the intellectual and cultural sophistication of this island society. Despite the enduring fascination, the most compelling mystery remains the movement of these massive stones. How did a relatively small population manage to transport tens of tons over uneven, sometimes treacherous landscapes? How did they prevent statues from toppling during transit? The answers to these questions have inspired a combination of field studies, experimental archaeology, and modern scientific analysis, revealing that the Rapa Nui may have possessed practical knowledge and technical expertise far beyond what was previously assumed for a society without modern technology. The Moai are not only monuments of stone, they are evidence of human ingenuity, coordination, and cultural expression etched into the very terrain of Easter Island. For centuries, scholars, explorers, and engineers have been captivated by the question of how the Rapa Nui moved the colossal Moai statues across their island. Each statue, some weighing over 80 tons, was carved with meticulous care from volcanic tuff or basalt, yet they were transported several kilometers from the quarries at Rano Raraku to ceremonial platforms known as ahu. The task is particularly astounding given the lack of wheels, draft animals, or metal tools, and the rugged, uneven terrain comprising hills, valleys, and dense vegetation. The logistical complexity alone challenges modern understanding of ancient engineering. Early theories often focused on the brute force solutions seemingly available to the Rapa Nui. One widely cited hypothesis suggested that the statues were rolled over a series of wooden logs functioning as primitive rollers. In this model, a team of dozens to hundreds of individuals would incrementally move the statue forward, relocating the logs from back to front in repeated cycles. While theoretically possible, this method raised questions about stability, especially when negotiating slopes or irregular terrain, and the risk of the statues toppling during transit remained significant. Another conventional hypothesis proposed dragging the Moai on sledges using ropes crafted from native plant fibers. Observers speculated that the islanders might have applied water or plant-based oils to reduce friction, creating a smoother surface for sliding. While experimental trials suggest such techniques could move medium-sized statues, short distances transporting the largest moai with this method would require extraordinary coordination and sustained energy, potentially involving hundreds of man-hours for even modest progress. A more recent and compelling idea involves the walking method, in which statues were rocked side to side, advancing incrementally with a combination of tensioned ropes and controlled momentum. Ethnographic accounts and oral traditions support the possibility that this technique was known and practiced by the Rapa Nui. Teams of workers would pull alternately on ropes attached to both sides of a statue, causing it to pivot slightly and step forward in a controlled motion. This hypothesis not only aligns with historical oral accounts, but also offers a feasible explanation for transporting statues over uneven terrain without the need for wheels or extensive mechanical apparatus. Archaeological surveys provide additional context. Parallel depressions, worn pathways, and residual ruts across the island suggest the repeated movement of heavy objects along designated routes, supporting theories of organized transportation. Traces of wooden rollers and rope fragments further bolster the idea that mechanical aids combined with human coordination played a central role. Additionally, the precise placement of moai along coastal ridges, inland plains, and ceremonial platforms indicates that the selection of routes was deliberate, reflecting a blend of technical problem-solving and social organization. Experimental archaeology has sought to replicate these methods with scaled replicas, confirming that each theory could work under controlled conditions. However, the walking technique has emerged as particularly promising, demonstrating that careful coordination, precise timing, and a fundamental understanding of balance and leverage could allow a small community to transport enormous statues effectively. These studies highlight the sophistication of Rapa Nui engineering and challenge earlier assumptions that such feats were impossible without advanced technology or outside intervention. The mystery of moving the moai, therefore, is not just a question of physical logistics, but a window into the intellectual and social capabilities of this remarkable society. In recent decades, modern researchers and engineers have turned to experimental archaeology to explore the feasibility of transporting the moai using the techniques inferred from traditional hypotheses. By creating full-scale replicas of moai statues, teams were able to test the effects of human coordination, leverage, and terrain on the movement of these enormous stones. Replicas ranged from smaller 1 to 3-ton models for initial trials, to mid-sized examples weighing up to 10 tons, providing a scaled perspective on the challenges faced by the Rapa Nui. One significant series of experiments focused on the walking method. Teams of 50 to 60 volunteers coordinated their efforts using ropes attached to each side of a replica statue. By alternately pulling and easing tension, the statues could pivot forward incrementally. Observations revealed that synchronization was critical. Even minor lapses in timing or uneven force distribution could result in the statue tilting dangerously. Force sensors attached to the ropes during trials measured tension peaks that reflected the precise balance needed, indicating that successful transportation required not only physical strength, but also advanced understanding of weight distribution, torque, and momentum management. Other trials examined rolling techniques using wooden logs or sledges. Volunteers simulated conditions that might have existed on the island, employing lubricants such as water or plant oils to reduce friction. Measurements confirmed that the coefficient of friction could decrease by up to 40%, making movement more feasible for medium-sized statues. However, even with lubrication, rolling remained challenging on slopes and uneven terrain, suggesting that the Rapa Nui had to plan paths carefully and may have selectively modified the environment to ease transport. Geographic and environmental studies complemented these experimental findings. High-resolution mapping of Rano Raraku Quarry and the surrounding terrain showed natural slopes that could assist in moving statues downhill, while coastal plains required careful pacing and coordination. Soil analysis along hypothesized transport routes revealed compacted tracks and depressions, consistent with repeated movement of heavy objects. In some areas, traces of wooden rollers and rope remnants were found, providing tangible archaeological support for the methods tested in modern trials. Energy expenditure calculations further highlight the magnitude of effort involved. Moving a single medium-sized moai over a few kilometers could require hundreds of man-hours, translating into months of communal labor for the largest statues. Such findings align with Rapa Nui oral traditions that emphasize synchronized chants and rituals during transport, likely serving to coordinate effort and maintain morale. Experimental replication thus provides a compelling argument that the feats accomplished by the Rapa Nui were possible through careful planning, skillful execution, and precise social coordination. These modern experiments underscore the remarkable sophistication of Rapa Nui engineering. By combining empirical testing, archaeological evidence, and cultural insights, researchers have reconstructed the likely processes employed to move the Moai. The results demonstrate that the Rapa Nui were not merely improvising. They systematically developed practical solutions grounded in observation, trial and error, and cumulative knowledge. Their achievements viewed through the lens of experimental archaeology reveal a civilization capable of engineering and logistical innovation that rivals other great ancient cultures. Understanding how the Rapa Nui transported the Moai requires a detailed examination of the materials, tools, and technical knowledge at their disposal. The statues were carved primarily from volcanic tuff, a relatively soft but dense material that allowed fine detail carving, while some larger or later moai were carved from harder basalt or scoria, which increased both durability and the difficulty of transportation. The islanders' stone tools, basalt chisels, handheld adzes, and stone picks enabled them to create precise features on the statues, from elongated ears and facial expressions to hands and torsos, showcasing both artistic skill and practical understanding of the stone's properties. Ropes made from plant fibers, such as totora reeds and hau trees, were essential for handling these massive figures. Experimental trials have demonstrated that braided ropes of sufficient thickness could withstand extraordinary tensile forces, particularly when tension was distributed evenly across multiple attachment points. When combined with the coordinated rocking or rolling of a statue, these ropes allowed the moai to be moved with controlled force, balancing the immense weight while preventing the risk of tipping or fracturing. Such understanding suggests empirical knowledge of stress strain and material limits passed down through generations. Friction and ground interaction were critical factors in movement. Archaeological studies of transport paths show evidence of compacted soil and deliberately flattened tracks. When wooden sledges or rollers were used, the coefficient of friction could be reduced significantly, especially if combined with lubrication from water or plant-based oils. Modern reconstructions confirm that such measures were essential to prevent statues from sticking or tipping over, especially on inclined terrain or uneven surfaces. Careful attention to slope pressure and contact surfaces would have been necessary to move the largest moai safely. Mechanical principles, whether explicitly understood or applied, intuitively governed the entire process. Volunteers in experimental archaeology projects learned to coordinate force rhythm and momentum precisely. Wooden pivot beams, rollers, and strategically placed ropes allowed the statues to pivot forward in controlled increments. This method effectively converted human energy into a system of torque, leverage, and balance, demonstrating an empirical mastery of mechanics without formalized knowledge. The Rapa Nui's ability to exploit these principles indicates a level of engineering sophistication that many early observers underestimated. Additionally, the interplay of tool use, rope tension, and terrain highlights the systematic approach taken by the Rapa Nui. Success depended not only on manpower but also on repeated practice, careful preparation of pathways, and intergenerational knowledge transfer. Observations from archaeological remains, including rope fibers, wooden fragments, and path compaction, suggest that the Rapa Nui developed these techniques over centuries, refining their approach based on experience and necessity. Transporting moai was therefore a complex integration of materials, science, mechanical insight, and human coordination, a testament to the advanced problem-solving capabilities of this remarkable society. Archaeological investigations across Easter Island have revealed surprising evidence that provides deeper insight into how the Rapa Nui managed the transport and placement of moai. Surveyors have documented parallel ruts, depressions, and worn pathways extending from quarries at Rano Raraku to ceremonial ahu platforms, suggesting repeated movement of massive stones along clearly defined routes. These features indicate not just improvisation but deliberate planning and environmental management, hinting at the complexity of logistics required to relocate statues weighing tens of tons. Excavations have also uncovered remnants of wooden rollers, rope fragments, and stone wedges embedded in the soil along these paths. The presence of these artifacts lends credibility to hypotheses involving rolling and sledging techniques, while subtle groove marks on the base of some statues suggest that rocking motions were also employed. Such grooves, when analyzed in conjunction with experimental archaeology, support the walking method theory, demonstrating that the Rapa Nui combined mechanical ingenuity with human coordination to achieve precise, controlled movement over considerable distances. The placement of Moai across the island further illuminates social and strategic dimensions. Coastal statues predominantly face inland, overseeing villages and acting as guardians, whereas inland Moai sometimes mark boundaries or ceremonial zones. This spatial arrangement suggests careful route selection and labor allocation, ensuring that statues were transported efficiently while fulfilling social and symbolic roles. High-precision leveling observed at some Ahu platforms underscores that placement was intentional and highly technical, requiring coordination and planning akin to modern engineering projects. In addition, the alignment of statues appears to reflect astronomical considerations. Some researchers have noted correlations between Moai orientation and solar or lunar events, implying that the movement and placement of the statues were intertwined with ritual and calendrical knowledge. Such patterns highlight the integration of practical engineering with cultural and spiritual priorities, emphasizing that transport was not merely a logistical challenge, but also a ceremonial undertaking. Collectively, these discoveries reinforce the notion that moving Moai was an enterprise combining empirical engineering, social organization, and ritual observance. Far from a simple or chaotic endeavor, each statue's journey required premeditated planning, the application of technical knowledge, and coordination of large groups of people. The physical evidence, the ruts, grooves, remnants of tools, and alignment patterns, offers tangible confirmation of what oral histories have long suggested, that the Rapa Nui developed sophisticated methods to address seemingly insurmountable challenges, blending practicality, innovation, and tradition in a truly remarkable fashion. The transportation of Moai was as much a social and cultural phenomenon as it was a technical challenge. Moving a statue weighing tens of tons required the coordinated effort of hundreds of people organized into specialized teams responsible for carving, path preparation, rope management, and guiding the Moai during transit. Elders and experienced craftsmen oversaw operations, ensuring that knowledge of materials, terrain, and timing was transmitted accurately across generations. This intergenerational transfer of practical engineering knowledge demonstrates that the Rapa Nui cultivated sophisticated organizational structures to support monumental projects. Oral traditions and ethnographic accounts describe synchronized chants, rhythmic movements, and ceremonial guidance during statue transport. These practices likely served a dual purpose, coordinating the physical efforts of large teams and reinforcing social cohesion. Chants and ritualized movements acted as natural metronomes, helping groups apply force in unison and maintain the correct rhythm, minimizing the risk of tilting or toppling statues. Such integration of social and spiritual practice into practical work illustrates the seamless blending of culture and technology. Labor was likely distributed strategically. Some community members specialized in carving and finishing the moai at quarries, while others prepared paths, cleared obstacles, or constructed temporary wooden structures such as rollers or pivot points. Rope teams coordinated the precise rocking or pulling of statues, applying knowledge of balance, torque, and weight distribution that had been refined over generations. Coordination of this scale required disciplined communication, trust, and a shared understanding of both the physical and ritual aspects of the task. Rituals and ceremonial timing also played a crucial role. Many Moai movements coincided with lunar or solar cycles, linking engineering projects with spiritual observances. The act of moving a statue may have been viewed as an offering or an invocation, connecting the community with ancestors and reinforcing societal hierarchies. By embedding technical labor within a framework of ceremony and belief, the Rapa Nui ensured sustained participation, motivation, and accuracy in tasks that could have been overwhelming purely from a physical perspective. Overall, the transportation of Moai illustrates a highly sophisticated social system where technical skill, communal effort, and ritualized practice coalesced. The Rapa Nui were not only capable engineers and artisans, they were masters of coordination, communication, and social organization, able to mobilize entire communities for projects of monumental scale. The blending of empirical problem-solving, ritual, and hierarchy underscores the integrated nature of knowledge and practice in Rapa Nui society, revealing that the achievement of moving and placing Moai was as much a triumph of human cooperation and culture as it was of mechanics and physics. Taken together, the archaeological, experimental, and cultural evidence illustrates the remarkable ingenuity of the Rapa Nui people. The transportation of Moai was not merely a feat of brute strength, it was the result of careful planning, empirical engineering, and sophisticated social coordination. By combining precise knowledge of stone properties, rope mechanics, leverage, and friction with coordinated human effort, The Rapa Nui were able to move statues weighing tens of tons across rugged terrain with astonishing success. The integration of ritual oral tradition and ceremony into practical work ensured synchronization and sustained participation, demonstrating that technical achievement was inseparable from cultural practice. The careful alignment of statues on coastal and inland platforms, the subtle grooves on the bases, and the compacted transport paths all highlight a civilization capable of combining observation, experimentation, and inherited knowledge over generations. Yet despite decades of study, questions remain. How did the Rapa Nui optimize their techniques for the largest statues? To what extent did ritual dictate movement strategies? Are there other, still undiscovered methods or traces that could further illuminate these processes? Like the granite of ancient Egypt, the Moai remain a testament to human ingenuity, revealing that sophisticated engineering, social organization, and cultural expression can emerge even in isolated and resource-limited environments. Waiting to be understood by observers willing to investigate closely,